mechanics working here. So let me begin by congratulating Jens for a wonderful career, for his many, many accomplishments at Topsoil, and for the continuation of his work in science. Now, I'm going to talk about an old topic. Fischer-Tropsch synthesis has been with us for 90 years and going strong. And those of you who have been through most of this, or much of this period, know that it has its ups and downs of interest. But in the last 15 years, for a variety of reasons, the interest again has reignited. In China, there's a great deal of interest in using coal because they have that as a natural resource, converting it into motor fuels. In the Middle East, and now increasingly in the United States, the abundance of natural gas has been the raw material from which you make synthesis gas and the Fischer-Tropsch products. And the interest in converting biomass to fuels has also encompassed as one of its options the conversion of the biomass into synthesis gas and the conversion of that product into Fischer-Tropsch products. So what I show you on the right here is a typical Fischer-Tropsch product with the labels for methane, liquefied petroleum gas, the light gases, the gasoline range products, diesel, and then the wax. And the wax, of course, can also be hydrocracked back into the diesel range to increase the yield of that product. The real question all along, and for industrial purposes, is how to get rid of the methane, or bring this well under 5%, typically today 3%, how to increase the yield of the diesel, and of course wax is acceptable because you can hydrocrack it backwards. And so there's been a lot of interest in finding promoters for doing this. Now one of the promoters that we have worked with, this is work done by Nielsen, who now works for BP, was to look at manganese oxide on cobalt, supported on silica. And what I show you here is both the unpromoted in red and the promoted material done at 1 atmosphere, 493 degrees Kelvin, that's 220 Celsius. And you can obviously see that when the promoter, because the manganese oxide is added, we have a reduction in the methane make and an increase in the C5 plus number. And if we go to 10 atmospheres, the reduction in the methane make is even more, and again you see the increase in the C5 plus. And what's also interesting is that this effect on the distribution is a function of the conversion, particularly at high pressure. This doesn't exist at low pressure, but at 10 atmospheres, you clearly see that as you go to higher and higher conversion, in the presence of the promoted material, you will eventually drop below 5% yield of methane, and correspondingly the red line shows that you go up towards 85 and 90% yield of C5 plus product. Now, the interesting thing comes up as to how does the manganese oxide alter the kinetics. And here we see that there's a fairly consistent pattern that if we hold the CO partial pressure at 1.5 bar and vary the hydrogen partial pressure, regardless of the manganese to cobalt ratio, there's a first order dependence on hydrogen. And a much more complex dependence on CO. Basically, in the absence of CO, the reaction doesn't occur, it then rises, or small increases in the partial pressure, and then eventually falls off. And if you look for an empirical correlation to all of these data, it can be found. You have in the numerator here the partial pressure of hydrogen times the partial pressure of CO, and in the denominator, 1 plus the constant times the partial pressure of CO, this quantity squared. And we can fit this equation to each one of these manganese to cobalt ratios. So the first question is, how do you rationalize the kind of rate expression we have? And this can be rationalized with a mechanism first proposed by Alexis and co-workers in 2010. CO and hydrogen can absorb CO non-dissociatively, hydrogen dissociatively. The CO then adds an atom of hydrogen to make 4-amyl. 4-amyl then is interacting with a second atom of hydrogen. At that point, the CO bond becomes sufficiently weak that you make the methine and the hydroxyl. And this is assumed to be the rate-limiting step. Everything consequently doesn't affect the consumption of CO. And this mechanism very naturally leads to the form that we see here. But now we can identify the constants A, B, here with these coefficients. This is actually the product of A and B. And B is the equilibrium constant for CO absorption. Now the question is, how do A and B vary with the manganese to cobalt ratio? And it turns out, if you look at the table, they vary in a very systematic way. B increases monotonically, as does A. So this infers two things which we'll need to check. One is the variation in B with increasing manganese suggests that adding manganese somehow strengthens the absorption of CO. The increase in A suggests that adding manganese oxide enhances the dissociation of CO. And so we want to look for evidence for this from independent experiments. So on the left, I show you the temperature for desorption of CO, linear CO, on this cobalt, for particles all of 10 nanometer size, but with varying amounts of manganese on them. And we can see that as we go from 0 to about a tenth manganese per cobalt, these are bulk ratios, there's an increase in the temperature from 440 to about 460, after which there's a plateau. So this is an indicator of increasing strength of CO absorption independently and experimentally, consistent with the trend that we see in the B parameter. Now on the right is an experiment carried out at reaction temperature, 220 degrees C. When we expose the catalyst just to CO, and we look at the amount of CO2 made as a function of time. And the lines are color-coded with increasing amounts of manganese. So here's the cobalt by itself. It makes a small amount of carbon. As you add more and more manganese, you get a higher and higher amount of carbon. Now you can look at the slope of these lines and get a rate. And ask, is this rate consistent with the observed rate of CO consumption under Fischer-Tropsch conditions? And the answer is no, it's too low. But what we're looking at is simply the Boulard reaction and not Fischer-Tropsch synthesis. But the two are related. And so what we interpret, first of all, for the Boulard reaction is that the manganese oxide, we presume, is sitting on the surface of the cobalt, and that there's an acid-base interaction between heavy-sorbed CO, which happens to be in the vicinity of the manganese oxide, so that the oxygen interacts with this Lewis acid center in the form of the cation. And this helps to rupture the carbon-oxygen bond. But clearly that's not enough for the rates to explain the rates of Fischer-Tropsch synthesis. So we further then suggest that we have cobalt on silica decorated with little patches of manganese oxide, and then hydrogen is added to the CO before the CO bond is ruptured. When the next atom of hydrogen is added, that's the point of CO rupture, but the manganese oxide facilitates that process. So we're going to ask, what evidence is there, first of all, that this model is right, that cobalt is in fact decorated by manganese oxide, and can we measure the fractional exposure of cobalt? Can we identify the oxidation state of manganese? And does manganese oxide affect the oxidation state of cobalt? That's one set of questions. The second will be, can we make direct observation of these patches of manganese oxide on cobalt? And I'm going to tell you the answer is yes to both of these questions. So the first one is to look at different loadings of manganese oxide, these are bulk ratios, and measure by Zangs and by temperature oxidation and reduction the fraction of cobalt that exists in the zero valence state. This is the active form of the cobalt after reduction. And interestingly, we notice that as you add more and more manganese oxide, the fraction of the cobalt there as cobalt metal declines from roughly 79% to 58%. So the manganese oxide is offsetting the presence of cobalt metal. And again, by measuring hydrogen chemisorption, we see that we have zero coverage in the absence of manganese oxide. We can quantitatively then measure the coverage starting at 9% going up to 83%. So at the very highest loading of manganese oxide, of the cobalt is in fact exposed. Then by doing Zangs and using a calibration here, we discovered that in the passivated state, manganese is up here, essentially at +4, so we have Mn equal 2. When we reduce the catalyst, it drops to this point over here, the green square, roughly Mn +2, or MnO. And when we put this catalyst under working conditions, it goes up slightly to about 2.3, 2.4 apparent oxidation state. That's the blue state, the blue circle here. So we can tell exactly what's the oxidation state of the manganese over here. And this cartoon, which we drew intuitively, is supported by the evidence that I'm circling over here. So that's the answers to the first set of questions. Now the second set of questions is, can we tell visually that the manganese is in contact with the cobalt? So if you take bright field TEM images, one is promoted and one is not, and if I leave off the labels, you would not be able to tell which catalyst is which. They look the same. And I should tell you that it's very hard to get images of this kind in bright field microscopy. Pride knows this very well, having done similar things. To get a good image of cobalt relative to silica takes a lot of artwork at the microscope, but it can be done. And you see here roughly 10 to 20 nanometer particles in both cases. Now I add the labels, and you know that the one on the right is promoted, but the one on the left is not. But there's not enough contrast to see the manganese, because manganese and cobalt are just 1 Z apart. Now we go to scanning transmission electron microscopy, high angle, angular dark field examination with EDS, so this is energy dispersive spectroscopy of the X-rays, and using a Bruker detector installed at the National Center for Electron Microscopy, we can begin to get sub-nanometer resolution, but according to the elements. And so here you see in green cobalt particles. That's a blow-up of this region of the dark field image here. You can see individual cobalt particles, and in red you can see where the manganese is. Some of the manganese is associated with cobalt, some is on the support. The blue here is the silica. Now it's a little bit easier to see where the manganese and the cobalt reside if you plot the colored pictures separately. So on the left is the cobalt, on the right is the manganese. And you can see that the manganese picture, the image, is somewhat fuzzier than the cobalt, meaning that it's partially spread out. Now at this point, one can say, yes, there's some overlap, but what we did was develop a set of softwares for image analysis. And this comes from image analysis of TV images, film images, and also looking at astrophysical images of stars. And we adapted this imaging. And so we could look at an image such as the one shown on the left and ask if we go around with all the particles and we average the particle to manganese to CO ratio on average on the particles, what's the distribution function look like? And that's what's shown over here. So this comes out, this sharp distribution function comes out of image analysis of images of this kind. And so for 0.1 bulk manganese to cobalt, we see the distribution. It's close to 0.1 with a spread. If we put on more manganese, of course, these distributions get They move to the right and they get broader and broader. I'll show you an example in a moment. But what this does do is it allows us to say that this cartoon has some semblance of reality. In fact, the manganese is in contact with the football. We can also use this kind of image analysis to ask how well distributed is the material as a function of how we pretreat the catalyst. So on the left is a catalyst, the very same catalyst, calcined at 400 C for 2 hours, then reduced at this temperature, and finally exposed at 220 for 6 hours. And then we can take the image here and we analyze it. And we see a fairly broad distribution. On the right is the very same catalyst, but it wasn't oxidized in advance. It was reduced for a total of 4 hours at 400 C, then exposed to hydrogen and CO, and we see a much narrower distribution. Now one might say, that's nice, but this isn't necessarily relevant to catalysis. But the answer is it is. On the left is the oxidized, on the left is the methane selectivity, on the right is the C5 plus selectivity. These are data taken in one bar. And what we're looking at then is the unpromoted catalyst, that's blue, so that's our reference point. The red is calcined and reduced, so we have a reduction in the methane. We get an even greater reduction in the methane if we don't oxidize the catalyst first and keep more of the manganese in contact with the cobalt. And conversely, you get a better C5 plus distribution, selectivity, if the catalyst is reduced directly rather than being oxidized. So all of this is by way of showing you that you can use advanced microscopic techniques to get evidence for how you've treated the catalyst and not just depend on hypothesis and your experimental data. Manganese isn't the only oxide we can do this with. More recently, we've worked with zirconium oxide. Here I'm showing you the plot on selectivity, C1, C5+. The blue circles are for the zirconium oxide. And you can see that in one atmosphere we can bring the C1 selectivity lower than we can with manganese oxide, and the C5+ considerably higher. And if we go to 10 atmospheres, the same holds, except the effects are even more dramatic. What about the distribution of one oxide versus another? And here we've chosen the point at which you get the optimal C5 plus selectivity, manganese on the left, zirconium oxide on the right. And the distributions that we back out of the TEM images, or the STEM images, show that you get a tighter distribution for the manganese oxide than for the zirconium. You have to use much more zirconium, 20 times more, to get the optimal, that's a better performer than manganese, but you get a broader distribution, say more of the zirconium oxide is now on silica support. How does this correlate also with the properties of the oxide used? So here I show you on the right the maximum C5 selectivity for unpromoted manganese we saw before, zirconium here, and then we've added lanthanum, cerium, and gadolinium oxides. And you see there's a very nice correlation here, and the descriptor is the promoter cation electronegativity. It turns out the activity also increases in this direction, also in a linear fashion. And this parallels very nicely with the Gabor Summershine and I and a co-worker, Alex Boffa, discovered in the early 90s working with titanium, zirconia, and other metal oxides on rhodium foils, where we could observe the distribution of the material by Auger spectroscopy and other means. And so here for CO, that was for CO2 hydrogenation. Here for CO hydrogenation, we see the same kind of trend and influence here of the electronegativity of the metal oxide. So this brings me to the end. So I've shown you specifically for manganese oxide and molten cobalt that we can decrease the C1 selectivity and increase the C5 selectivity by adding more and more manganese oxide. This effect is demonstrated to be associated with the stronger chemisorption of CO. It also is due to the increase in dissociation of CO, which is further facilitated by the presence of hydrogen. STEM EDS shows that the manganese is associated with the cobalt, and the less manganese we put on, the narrower the distribution, the more manganese, the more goes on the support. And finally, I've shown you that the promoting effects are not limited to manganese oxide, but also extend to zirconia and other things. So finally, I want to thank the people who did this work. Arne Dinstedt was the first graduate student who worked on this. He was followed by Sebastian Werner, who was a postdoc, who's now back in Germany. And the current work is being done by Gregory Johnson, the second graduate student. All this work was supported by UP. So thank you very much for this opportunity to come and celebrate Nielsen's accomplishments, and thank you for your attention.
Thank you very much. Questions? Yes, there's one.
I'm just curious why you picked manganese. Maybe lattice matching have something to do with it?
No, actually, we looked in the literature at the time we were starting this work. There could have been various choices. We could have looked at titania, we could have looked at zirconia, manganese had been tried by various people, and I think we were drawn towards manganese because Bert Beckhuizen had just recently published some work on this.
I wonder, we think that the surface of cobalt catalysis is to some extent dynamic structure, depending on the CO partial pressure and developing with time. And so far, and having a nice little cobalt crystal and developing the picture on that, I don't see that these things come together.
Okay, so we have to first of all define what we mean by dynamic. So I've read your papers on this. So I think what you mean by that is that the surface of the crystals reconstructs depending on the temperature and hydrogen to CO ratio and total pressure. And I think that's certainly true. We don't say anything about that here. All we say is that you have crystallites of cobalt, and you see them before and after catalysis. Obviously, we don't observe them under catalysis at 10 bar and 220 C. And we do see the promoter associated with the surface. And while we are not looking at the particles under working conditions, Alvarado conditions, nevertheless, I think we can draw meaningful inferences from the ex-situ observations that we make by Zanes and by TEM study. But I don't deny the fact that things change under reaction conditions. Yeah.
Do you have any information about the size of the manganese, the configuration of the manganese? Is it some spherical particle, or is it flat coverage?
That we would love to know, but we don't. We don't have the resolution. Remember, we have roughly 1 nanometer resolution, elemental resolution, and we have 10 nanometer particles. The microscope resolution, best microscope resolution is half an angstrom. So we can see lattice fringes, but we can't see elements with that same resolution. And this is really the state of the art for STEM EDS. It doesn't get any better than this that I know of. We have recently moved to looking at alumina host particles, or silica host particles that are perfectly spherical, and depositing the crystallites on top. Now you can look at the edge of one of these 10 nanometer particles. But even so, while you can see the manganese or the zirconia, you can't tell the shape. You don't have that resolution. So we get close, but not close enough. Yeah?
How does this compare with the industrial cobalt catalyst? Is this better than what you're getting?
This is comparable in productivity. If you ask them how many kilograms of product you make per kilogram of catalyst, it's comparable numbers. It's not better. It's as good, but we're not trying to optimize. We're trying to get a better physical picture.
So I was also curious about your PM images. Normally when you look at cobalt, it tends to form a surface oxide. And your images seem to show a very sharp, clean surface. Were they reduced? And then
Okay, that's a good question. So some of the images we've taken are really COO, cobalt in its oxidized phase, right? Because as you know, particles of cobalt oxidize immediately when you take them in the atmosphere. We have done, though, since we can't reduce this material with the microscopes that we have done reduction offline in the laboratory on the side of the microscope. Put this in a sealed bag and quickly mounted the probe in the microscope. And now when we look at the images, you can see that the lens spacings are that metallic cobalt, largely, not completely. It's taking some effort to convince the people in NSEM they should invest in an atmospheric probe. But we're working on it.
Yes?
So, how the result is depending on the amount of magnesium added in the catalysis?
I don't understand the question.
I mean, the result or the activity or selectivity depends on the amount of the magnesium added.
Oh, okay. So the activity goes up with manganese, and then if you put too much on, per gram of catalyst, it falls off because you're now masking more and more of the cobalt. So once you bury the cobalt in manganese oxide, it's inactive. We also know that if you put in manganese oxide on silica with the same emulsion, we have no activity for Fischer Tropsch, and we don't conserve any CO. So manganese oxide per se is inert to CO consorption chemistry.
I thought we had seen in some other presentations that the selectivity goes better as you go to higher and higher conversions.
Yes, I showed that.
And do you have an explanation for why that happens?
Yes, it has to do, let me see if I can back up quickly here. Right there. So, if you look at this rate expression, it is actually changing as you go to high pressure. So as you go to high pressure, the second term in the denominator dominates over the 1. So you get B squared partial pressure of CO squared. That cancels a B in the numerator and a CO in the numerator. So now you have A over B, partial pressure of hydrogen to CO. Now your consumption ratio isn't exactly your feed ratio. So you're getting richer in CO relative to hydrogen as you go to higher conversion, so it turns out. And as you go down in hydrogen relative to CO, you'll go a little more C5+. So that's our interpretation that you see here. Or what you see on the next one slide back. So it's all self-consistent.
Any more questions? Yes, there's one there.
Does the promoter also has an effect in reducing coke and wax, the high molecular, the more polymeric molecules?
Yes, you get more polymer and more manganese or zirconium you put on. And the way we explain that is that if you facilitate rupture of the CO bond, then you get a faster rate of producing CHX. I don't know how to define X, but CHX units are part of what enters into the polymerization to make higher molecular weight products. So you do two things. You produce, you change the balance of hydrogen to CO on the surface in favor of CO. So that reduces the hydrogen make, and you increase the CHX coverage. All of these work in the direction towards polymerization and making less low molecular weight. So they work together.
Okay, if no further questions, I think we'll thank you again.